All right, today we're going to talk about section 4 of chapter 2, the last section. Because after this, pretty much every section that we're going to cover, every chapter we cover only has 3 sections in it, 2 or 3. So we'll be going pretty quick from here on out. This section is created into 3 parts. Part 1 will discuss correlation and the scatter plot. Part 2 will deal with the linear correlation coefficient, R. And part 3 will discuss linear regression.
There's some internet coefficients.
The linear correlation coefficient R, which we will refer to as the R value. Simply by the term correlation, what does correlation mean to you?
Kind of go hand in hand.
Yeah, they relate to each other somehow. Either they do or they don't. That's pretty much what we're getting to. Either the data is correlated or it's not. What we're going to looking at here is our data will consist of 2 possibly unrelated characteristics. The population and will be arranged in ordered pairs, which we call paired data. Okay, that's a really quick question from algebra. What does ordered pair mean? No, there's no E there. It's just pairs. What is an ordered pair? Remember, it's the same thing as paired data. Think about the graphs in algebra. What is this horizontal axis called? Or what would it's the x-axis and the vertical? So if we had a piece of data right there, what would be its location? XY. That is what we call pair data. So this is how we're going to go about looking at, are the data correlated? So after we have our scatter plot, we have all these dots all over the place. The way that the dots are arranged and the compactness of them is what we're going to be finding out here. That's what the R value is, the correlation coefficient is going to tell us how compact the data is. In other words, how close to a straight line. Remember that now?
Now, like, whenever you try to when you do the graph,
Yes. Yes, that's exactly what Excel does. Yes, yes, that's exactly what it is. Very good. Very yes. That's exactly what correlation is. Is the correlation values the coefficient R ranges from -1 to 1. Okay, now let's look at what do you think these mean? That's what we just said. It's the relationship. A correlation is a relationship between the X and Y data. If it's -1, what does that mean? No. No. Well, the inverse would be what? They're not all over the place. Actually, if it was -1, it would be an exactly straight line. All the data would be an exact straight line. So if it equals -1, it's a straight line going down. If it's +1, then it's a straight line going up. And if it's 0, there's no correlation. The data is just spread out everywhere. See if I have any pictures. Yeah, we'll look at some pictures in the examples. So actually, if you think about it, the correlation coefficient R is the same thing as the slope. If it's negative, it goes down. If it's positive, it goes up. And anything else between there, between -1 and 0 and 0 and 1, the dots start getting further away from the line. But you can, the bigger the decimal is, the closer it is to the line, and it spreads further and further out. So until it goes from this to that, and then it gets back to being close together. It goes from this to this. So that's what the correlation. That's so it's we can look at we're actually looking at the slope. Let's look at the definitions here. When we talk about correlation, we talk about the relationship of one variable to another. Linear, this is what we're looking for. Linear correlation is a correlation between two variables that have a graphic representation close to that of a straight line. Hence linear. Now, when I say the graphic representation, what graph do we use? What kind of graph? What's the name of it? We use a scatter plot, or it's also called a scatter diagram. Why do we use that? We use a scatter plot. I'm gonna define what it is. Well, this is why. Because it's a plot of paired quantitative data in the form of X, Y. So again, we use the scatter plot because remember, we have 2 bits of data that are either related or they're not related. We don't know. We just have 2 bits of data, and we don't. Each one of the pairs are associated with each other. We see how they relate. We don't pick one from X and another one from Y. No, they have to be even pairs. Once we do that, the only way we can relate them is by putting them in dots, each pair separately. So we graph each ordered pair of data separately. To visually determine whether a relationship or relationship is correlation exists between the 2 data. Sources.
The wires turned around, would that make the house incorrect?
What's that?
X and the wires turned around, would it make?
I'm glad you said that. If there's a relationship between the data, would it matter in which order you put it? No. If there's a relationship, there's a relationship. You can't say, okay, just because you came first and you work, but it doesn't work the other way. So it doesn't matter. So that's the beauty of this using a scatter plot. It doesn't matter how you do it. Because if you think about it, if you take the scatter plot graph, what's that? No, it's just it's transposition. It's just so, or I could take it like this. If the data is not related, it's not related. But if the data is related, it's still related. Only thing that's going to change is the sign of the value R. So that's a very good question. So you don't have to worry about how you which one you put, but typically you look at see what can relate to each other. We're going to look at examples from the data in the back of the book. That looks at what was that? Weight and arm circumference. So the more you weigh, the bigger your arms are. That's true. Whether it's muscles or not, it gets bigger. I mean, think about it. If you had a 600-pound body and your arms were still normal size, you look like a stick man. So body grows proportionally. Also, we said this last chapter, we'll say it again. We said causation does not imply correlation. That's from chapter 1. Because when the cause of something doesn't mean that there's a relationship. In chapter 2, it's just the other way. Correlation does not imply causation. I mean, just because there's a correlation between the graphs, between the numbers, doesn't mean that there's a cause that made it so. It just happens. All right, so let's look at the first two examples. The examples that we're going to be using come from this. This is data set 1 from Appendix B in your book, where it had all these things. This is how you do a data analysis. All of these variables is what you're examining. These are the values of it. Why so many? You have the age of the person, you have their pulse rate, diastolic and systolic, you have their gender, you have the HDL and LDL. What are HDL and LDL? Which one's good? Yeah, L is for lousy. H is H, L is lousy. That's the bad cholesterol. That's the good cholesterol. You have the white blood cells, you have the red blood cells. What do red and white blood cells do? Diseases and how it carries your antigens, but it also is oxygenation. The white blood cells are the oxygenation, and red blood cells is to carry nutrients to the rest of your body. Platelets. And where is blood created? Very good. Very good. Yes. The bone marrow. If you ever had a bone marrow transfusion, wow. That's when they take a needle and they have to bore it into your bone first. And then they have to suck out the marrow from there or inject new marrow. Yes, this is exactly where it is. Very few people remember that, where it starts from. The weight, the height of the individual, of the subject, their waist circumference, and their arm circumference. BMI, the basal metabolism rate, the basal metabolism index, the body mass index. It tells how your body, is it healthy or not, which you look at. So you have all these. Here's exactly only 5 of the data. Why do you have so many pieces of data then? Why would you collect so many data? Because if you were looking at the first example, we're going to look at the waist size, the circumference of the body waist, their hip girth, and their arm circumference. If that's all you needed, why not just collect that? Or if you're going to do some other correlation, Because what if you wanted to know if there is a correlation between the person's diastolic or systolic, or between those two? What is diastolic and systolic blood pressure? You go to a doctor's office. When they take your blood pressure, what's the normal blood pressure? Right. That's the diastolic over the systolic. What they represent is, okay, when they put that thing on your arm, the sphygmomanometer, the blood pressure cuff, they squeeze it, squeeze it. What does it do to your body, to your arm? So it blocks off the circulation of your arm. So what they do is then they listen, that they always put an ear thing, the sphygmometer to your forearm here, or your joint. What they're doing so is as they release air slowly, they're waiting to see until the first time they hear a pulse. That's when the vein is open wide enough so blood can start going through. That's the first number. Then they keep on loosening it up until they can't hear that anymore. All the blood's flowing normal now. That's the systolic. So it tells you how thick are your arteries and how good is your blood flow. The better all this stuff is, that's the reason it opens at 120 mercury per centigram or something like that. So that's what that's looking at. What we're looking for is our first bit of data is we're looking at the waist and circumference. I threw in these because after I find this stuff, I just want to see you do an analysis of men versus women. You can compare them, the two. So let's look at this, what it would look like. The data actually spit out this. This is the data set for all the data points of the waist and arm circumference of the individuals, of the subjects. So what do you see there? What do you notice about those the waist and correlation arm, the correlation data? Is it close to a linear? Do you see a pattern? Because why would we want to know what the correlation regression are? Why would we know that number? What's just important about it? Well, no, if we know that this does have a very low correlation, but there is a correlation. Well, there's another thing I'll get to talk to you about, but no, it's not how that's another study you could do. You can see, does the circumference of the waist have relationship to the number of heart attacks, if any of the person experienced, or strokes? No, what you want to do is if you have the R value and how close it is to zero, then you are that certain you can predict future occurrences. So if I find out what the R value is and know that that's like 0.6 or 0.7, then I'm 70% sure I can calculate what, if somebody has a waist of 200 centimeters, I can pretty much predict what their arm circumference is going to be. That's what this whole thing's about. So we can come up with an equation to predict future occurrences. So that's the whole thing. This one does have a regression because slowly these points are rising up, going up. So is it a positive or negative correlation? Positive correlation, yes. Okay, the next example, we're going to look at the weight and the pulse rate, the blood pulse rate. And this is what the data would look like. What do you notice there? All over the place. So this one, we can't determine if there's a relationship between the data anywhere. So again, each one of these dots represents what? An individual person, their weight in kilograms and their pulse rate. But look at this guy. He's only 50 years old and his pulse rate is in the 100. What does that tell you? This guy's here is very unhealthy. When we say about heart attack, this person's ready for a heart attack or a stroke. And don't think that because you're young and you're healthy, I've always passed every one of my physicals. Every physical. But one time I was in a rear end accident. I went to the doctor for an x-ray of my neck. And they noticed your neck is great, but your heart is enlarged. So said, go see a cardiologist. I would. And what happens in the heart, you have three main arteries that go from the heart and feeds itself because it needs blood to exist. The doctor said, yes, one of your arteries out of your heart are 100% blocked. Another one is 80% blocked, which means only one artery is pumping blood to my heart, which is why you see all these athletes that are top shape. They're running or walking, and all of a sudden they plop down. And when that happens, the minute they hit the floor, they're dead. The second they hit the floor, because what happens there is the arteries, the tubes that go out of your heart, one of them ruptured. And the second that happens, you lose all blood pressure at your body, and there's no way you can fix it. This is exactly what they call it, Widowmaker. And that's why I tell everybody. I mean, I don't care if you think you're healthy or not, if you could run up the stairs or not, go get your heart checked at least once or twice in your lifetime to see how it behaves. Because what they did there is they did x-rays of it and they started to notice some stuff, but they had to go through my vein in my upper thigh. And they put a camera in there up to my heart. And that's where they did everything. You're knocked out, of course, all this stuff. You don't know what's going on. But they can see exactly how clogged your arteries are and everything like that. So, yeah, I know if y'all like eating hamburgers and French fries and stuff like that, like I did. I mean, again, I used to climb mountains. I still scuba dive, mountain climb, ski, hike, camp. I did any sport you can think of. Pretty much, I've done it. And I said, so I passed all my physicals. Since that one time, if it wasn't for that, I'd probably be dead right now. Because I'd still be doing stupid stuff, eating hamburgers, pizzas. So anything that has grease in it, that goes somewhere. Your body absorbs it and goes straight into your arteries. So that's a public service announcement: is eat more greens, more fiber, and exercise regularly, and drink a lot of water. Okay, we have another example here. What do you think year? I'm trying to ask you before I put this up there. Oh, this is not about people. This is another data set of pennies. Do you think all pennies weigh the same? Why not? What would that have to do with it? Very good. This is what the data of pennies, if you weighed them, their weight is either down here or up here, and the year they were minted has a lot to do with it. Very good. Very few people ever think a penny is a penny. No. Same thing with nickels. If you look at the side of, if you take a nickel, hold it on the side, you can see a line between the two types of metals they have in there. Same thing there. The year they were minted, depends on how much silver, how much zinc they have in there. That's what this is. That's what this shows us. The data shows us that the newer pennies are lighter weight. The older pennies are heavier. But we're also looking at in grams, looking from 2.5 to 3.1. We're looking at 0.6 of a gram. That's very light. You couldn't tell that by just holding it. So again, if you see this, is there a correlation? Well, you think, okay, if you draw a line like this, which means that the heavier it is, the older it is. Would you be true? Yeah. But it's not, there's no correlation there because this group of data and this group of data have their own information about it. I think these old ones were made with 90%, 7% copper, 3% zinc. These were made up of 97 or 98.5% zinc and nothing copper. Why? Because copper is an expensive mineral, or not mineral, but a metal. Okay, so those are those pieces of data. Let me see. I got that data. Right, that example. Okay, yeah. Oops, I made that one. Let's look at part 2. We talked about correlation. These are linear correlation. The coefficient R, also called the R value. This is a mathematical way. Now we're going to look at the algebra of doing all this stuff. The first part 1, we looked at scatter plots. We looked at see how all this data was gathered, and then from there we estimated what the value was. Now in this section we're going to calculate it algebraically. Actually, typically that's not done. Typically we use computers or software that does it for us, but I'm going to show you how to do it manually so you have a better idea of what's going on. And remember, in chapter 1 we said if you have fewer than 20 pieces of data, don't draw a graph, do it by hand. It will take you as much time to put all this stuff in to a computer as it was to do it by hand. And you'll see that it's not really that difficult. Okay, so the definition of linear correlation coefficient. Linear correlation coefficient R is the measure of the strength of a linear correlation between two variables. So again, it's the measure. It's the algebraic calculation of the relationship of the two variables. Remember, what should the values be? What should the values of R be? So what's the range? What's the spread of R? -1 to 1. Inclusive, you can use the endpoints. If it's -1 or 1, then there's 100% correlation between the two. If there's 0, there's 100% no correlation between the two. Anything else is the gradient of that correlation.
Let me ask you a quick question.
Yes.
It's been forever since I asked that, but what does the derivations in the middle of that mean?
These,
Yeah.
what this says is R, the value of R or can be greater than or equal to -1 or less than or equal to +1. It could be anything between there. Not or, it's got to be and, because it has to be between -1 and 1. There's no if, ands, or buts about it. The way we describe it is if R is close to -1, then there appears to be a negative correlation between the two variables. And if R is close to +1, then there appears to be a, well, I should put, let me put, there appears to be a very strong, because the closer you get to -1 and +1, the relationship is very strong. And the further it goes from -1 and 1, it becomes very strong, somewhat strong, weak, and none. So there are all these gradients. Again, this is the subjective part. This is the subjective part. Okay, I get a value. I calculate R. What does it mean? Is it a strong? Is it a weak? Is it what? So that's what we have to look at also. And we're going to be using something in this chapter that we won't get to until the very end of the course, the z-scores. So let's look at the data here. So the following plot of data is from the data set in the back of the book. It isn't clear whether there's a correlation or not. Why not? So what do you think if it's somewhat very weak, what do you think the R value is of this graph? Because without this outlier here, it looks pretty good. Ideally, yes. Outliers ruin your correlation R. So if you have an outlier, get rid of it. But then now that also change, if you get rid of any piece of data in your data set, you dramatically change the value of R. So now, since you got rid of a data set, is it a true representation of the data? So again, so there you have the inaccuracies of statistics and probability. So if you were to give this an R value, what would it be? Positive or negative? Positive. Is it close to 0 or close to 1? So you're saying it's larger than 0.5 or less than 0.5? Yeah, the actual data set using StatDisk says that the correlation coefficient R is 0.591, which means that it's very, very, very far spread apart, but there's a distinct pattern, positive pattern. Yeah, then we're looking at something called a p-value. So again, this is all where the computers and calculators come about. But yep, that's what we're gonna do right now. So let me here. I have two of them because we're going to do two different sets of data, two different calculations. Here we have our data. So go ahead and write this down on your sheet. What I'm gonna start doing is in the future, whenever I have tables and stuff like that, I'm gonna make up copies and give them to y'all so you have them, so you have at least line graphs and everything. So we're only going to use these pieces of data. What does this data represent? What does it tell us? What is it asking us? Is there a correlation between the amount of chocolate Nobel laureates eat? Well, that's what we're going to find out.
Oh,
Again, never, if it's numerical, never take a guess. Because if you said no, I said, okay, then why not? The question why is always going to be asked when you do statistics. Why is that value there? Why? Where did it come from? Why? If you can't answer it, the second you can't answer it, your study is wasted and gone, thrown away in the trash. Goodbye. So here we got this written down, and this little table down here. Because the first column is our X values. The second column is our Y values. So we have to decide the top ones are X, the bottom ones are Y. So we'll put the values in there. We had 5, 6, 6, 9, 4, 3, 4, 2, 5, 11. So each one of these are their own ordered pairs. So each one of these would create a dot in our graph. So our ordered pairs would be X, Y. Here is our formula for calculating R. Oops. Okay, I'll screw it down in a second. What does N represent?
oh,
The number of samples. N represents the number of samples. N times, what does that symbol mean? Summation. Yeah, summa. So it means summation. That means add up whatever the next part is. So what do we do in this first one? What does it tell us to do there? Multiply X times Y and then add all of them up. That's what it says. Then the summation of X times the summation of Y.
so is this like a standard formula for this or?
Oh, this is the formula, yeah. There's only one formula. And on the bottom, our denominator is N times the summation of X squared minus the summation of X squared That's the first part. And now we do the same thing, but with y's.
So this kind of goes back to the beginning when you said that the letter could represent a number.
What's that?
You know, in the beginning, you talked about letters.
Represent numbers. Yes, yes.
Okay.
Because there's no way you can write. Remember, our accurate data, our accurate study would require a whole bunch of data. I'm not going to write a formula that has each one individually. So this one represents all my data. Now, this formula tells us what we need to find. How do we find n? Yeah, just add, how many ordered pairs do we have? Because if you notice on the bottom, both of these are identical, except this is x's, this is the y's. And so our ordered pairs, here's 1, 2, 3, 4, 5. So this is what n equals. Our n is 5.
Have you come up with it?
Count them. Look, I just labeled it. How many ordered pairs do I have?
Oh, I see.
Looking at our formula, how do I find this value? Yeah. Add up all of my x's. So you get 5 plus 5 is 10, plus 10 plus 4 is 24. So this is column A, the sum of column A. This one, the summation of y, is column B. This value down here. So I add up all my y values. 11 plus 9 is 20. 6, 29, plus 2 is 31. Finish the top. I need to find this value. I'll call that C. So column C is going to be what? I multiply x times y. Because that's what this tells me. I multiply x times y first. Order of operation has to exist. What comes first, addition or multiplication? So we multiply first, and then we add up all the numbers. So 5 times 6 is 30. 6 times 9, 54. 4 times 3 is 12. 4 times 2 is 8. 5 times 11, 55. So now, since we have all the x times y's, I have to add up all the x times y's. 12 plus 8 is 20. 20 plus 30 is 50. Plus 54 is 104. Plus 55 is 159. What else do we need to find before we calculate our final answer? Yeah, we have to find x squared. We'll put that in line D. So this is x squared. So we have to take all the x's and square them. So 5 squared is 25. 6 squared is 36. 4 squared, 16. 4 squared is 16. And 5 squared is 25. So now I add up all my x squares. Ten plus 18 is 28. 2, 4, 6, 8, 10, 11. 118. What's the next thing we got to find? Yep, we have to find the y squared. That's column E. So I go to the y column. I square those. 6 squared, 36. 9 squared, 81. 3 squared is 9. 2 squared is 4. 11 squared is 121. 251. Add up all those, I get 251. I'll wait for everybody there. So is everybody okay where we got all these numbers? Okay, the only thing we didn't calculate is this one and this one. Where do we get those numbers? This one and this one. Do we have to create those columns? Why not? Well, we have the summation of x. All we have to do is square it. Whatever this number is here, I put it in there and I square it. So this inside square root of x is already done. It's right here. This one, the summation of y is already done. Okay, so we have everything calculated. I mean, yeah, all the columns done. Let's begin. Plug and play. So n was 5. Summation of x times y, 159. The summation of x, I'm sorry, I'll go ahead and put it up there because y'all have the numbers there. The summation of x is 24. The summation of y is 31. All over the square root of the first parentheses. N is 5. Summation of x squared is 118. Minus 24 squared. That's the first parenthesis. And the same thing with the second. 5 summation of y squared is 251 minus 31 squared. Close that. And it's the square root of all of that. Check out those. But you should have everything. You should have everything there in yours. You should have all these numbers in yours. I need this for people.
Oh, okay.
You can't see the bottom of the screen. Now comes the algebra part. 5 times 159. Yeah, 795. Minus 24 times 31.
What?
24 times 3 is
Oh.
720 plus 744. So that's the top part. Now the bottom part. Inside the first parenthesis. 5 times 118. 590, yes. 24 squared. 556. 76. Five times 251. 1255, yeah. 31 squared. 'So what are we gonna top? 795 minus 44 is 51. 590 minus 576 is 14. 1255 minus 961. 194, isn't it? No, let's see. It's 294. $51. So 14 times 294. And what? 4,160. Oh, 16. Oops, yeah. So it's 4,116. The square root of 4,116 can't be 2,000.
Huh?
Can't be 2,000.
Oh, it's 150 or 180.
64 point. They give me 3 decimal places.
156.
Okay, now whenever we do this stuff, it'll be shown later on, but we use 3 decimal places because all our tables we'll use later on in the back are rounded to 3 decimal places. So yeah, it's so rounded, always rounded numbers to 3 decimal places for accuracy. So our value was 795, which is what it was earlier, wasn't it? Yeah. So that's one way of doing it. Complex? Not really. All it is multiplying and adding. It's time consuming. If you had anything more than up to 20 is okay because that you can add that many and use calculator and do that. But yeah, anything more than 20 pieces of data, if it's not intervals, then you're okay. If you have interval data, then you have to find the midpoint of the sets of data to find these calculations. Okay. So that's one method of solving it. You don't need you don't need a computer to do anything. This is the way we used to do it forever. The second way of doing it, the same data set. And get these use the table in the back of the book. So we still have 5, 6, 6, 9, 4, 3, 4, 2. Because yeah, I'm pairing off all these like this. The second method is uses the z-score of the data. So the formula to find R of this one is the summation of zx times zy over n minus 1. Those are z's. My z's have a line through them to separate them from 2's. So your question should be, what exactly is a z-score? Good question. It's going to use two things that we haven't discussed yet. That'll be discussed next chapter. No. The practice? This formula is used in it because we can find the average rate of change of the data set. That's what we do. So anytime you have a line, you're looking for the slope of the line at a certain point, and that's what you find derivatives for. Yes. So how do you find the z value? The formula for the z-score is this: x minus x bar over s of x. This is the z of x. Then we find the z of y minus y bar over s of y.
What's the bar?
That's what I'll get to in a second.
Oh,
These values of z, once we do this algebraic part, we have to go to this table in back and look at, okay, I have my n here, I have my value here. What is the z coefficient correlation to it? So these are just the algebraic part. We have to go back in the tables and do this, but we're gonna do this as the semester goes on. X bar is the average of x, or the average, another name for it is called the mean. And the y bar is the average of the y values. How do you find the average? Yep. Add up all your data, all your x's, and divide by how many you have. Again, that's super easy. S sub x is the standard deviation of X and standard deviation of Y. What do you think what does deviation mean?
The average.
Standard deviation is the standard deviation is that it's a deviation simply means how far something is off a course. If you're on a boat and you're supposed to head north, but you're actually heading northeast, your deviation is how far you're going off the north course. The standard deviation is how far is each data point away from the average. And well, I don't want to ruin the surprise. The example I'm going to give you next week is how do you determine which paint brand is better? That's what we're going to talk about next week. So what we would do is we'd find the summation of this, then find the average, find the summation of this, find the average, plug them into our formula, find the standard deviation of X and Y, and find the z-scores. Once we find the z-scores, we'd multiply them together, then add them up, and divide by n-1. The reason we use n-1 is because it removes any anomalies in the data. We basically, that's the get rid of that one anomaly type thing. Yeah, again, it seems like a lot of stuff right now, but it'll make a lot more sense next week when we start doing this step by step by step. Because next week we start calculating. But this is another way we could do it that uses tables, and it's going to give us the same value. Our R is going to be the same thing. What was it? 7, 9. What was the last one? 5. It's going to give us the exact same answer, but in a different way of doing it. Because bottom line is you don't need computers to do all the work for you. Because what if you're doing a research and you're out in the field and your battery died? You can't do anything. But if you have everything written down, as long as you have ink in a pen or lead in a pencil, you could do the work. Yeah, because when I took stats back in the 80s, early 80s, we never used calculators. We just used pencil and paper. What's that?
How long were you notes?
How long did I what?
For your notes?
The standard deviation is once you see it, it's super. I mean, the formula is super simple. So my notes, my notes I took what the professor put up there and abbreviated them. I got rid of all the fluff stuff. Here's a formula. This is what it means. This is what each of the part means. So because I hate writing, as you see, I can't. After a couple of days, I can't read my own handwriting. So that's why I apologize to y'all in advance. Okay, let's see what else we're going to talk about today. Oh, yeah. Because in that chart we saw earlier, we talked about a p-value. Or determining. Linear correlation. See, a p-value is a whole nother process in itself, which I don't want to get into right now. But there's another way we can do it. What we're looking at here is we have our data. we have the values of 1, -1. We call something called a critical value. In calculus, we use critical values to find out where our functions are going to do something, whether you start going up and down, or if they're going to bend up and down. So we find a critical value. The critical value is, again, it's a number in the chart that we'll use in the near future. Indicates it's a number that indicates the, I'll use significance. It's the number to use significance of the correlation. So, okay, our value, for example, was 0.795. Let's see, the critical value we came up with was, if our critical value was 0.8113 or 811. So we do there is we put 0.811 here, and then we also look at the negative side, negative 0.811. So that's what we do before we find the R. Once we find the R, if the R value falls between these critical values, then there's no correlation between the data. If it falls in here or here, then there is a correlation. So our R value is 0.791, which is right about there. So is there a correlation? No. Even though the graph looked kind of spread out, this takes away our objectiveness. Because remember, earlier we talked about is close to or close enough. This takes away all doubt about it. Is it close enough? Well, mathematically it says no. We're actually 0.795. 0.795 is very close to 0.811, but it's on the wrong side of it. So it's got to be in these bounds here. Again, when we start dealing with standard deviations and things like that, I'll explain to you what this stuff means. And we're going to need to know this on whether we keep or reject hypothesis at the very end of the course, when we start doing actual testing our hypotheses. So if there is, let me put it on top. No linear correlation between the two variables, the probability of getting paired sample data or data from your sample with a linear correlation coefficient R that is at least extreme as 0.811. No, from our data is 795 that we obtained our data, our sample paired data. So if there's no linear correlation between the two variables, the probability of getting paired sample data with a linear coefficient R that is at least extreme as, in other words, at least as, if not greater than, that are obtained from our sample data. That's what the p-value is all about. So that's what the p-value tells us. Yeah. So what does all that stuff mean? Interpreting the p-value. Only a small p-value, typically we use 0.05, suggests that the sample result are not likely to occur by chance. When there is no linear correlation. Only a small p-value 0.05 suggests that the sample results are not likely to occur by chance when there's no linear correlation. So small p-values support a conclusion that there is a linear correlation between the two data sets. Let's see if I have an example sheet. Here's an example of what Terry finishes. This next example will examine a correlation between shoe print lengths and height. What would be your hypothesis? The shoe print length versus height. Is there a correlation? Basically it says what? The taller you are, the bigger foot you have. That should be. But according to this data, there's some weird people out there. But no, there is a correlation, but this person who's pretty short got a pretty big foot. And this person's tall has got a pretty short. So, but again, these, you would think twice about them, they could be outliers. But there is a correlation here. The correlation to this one is 0.813. It all depends on what the p-value is. The closer p gets to 0, the better it is for us. And this one is, so we can say that there is a correlation length. It's just that these three are going to be deemed as anomalies or outliers. Okay, the last thing we're going to talk about, regression. So for this one is when we conclude that there is a linear correlation between two data sets. The variables. We can find the equation of the line that best fits the data. Notice best fits, I made it in bold because that's what we're looking for. This is what we call a best fit line. Because remember, don't get all these terms mixed up. We talked about correlation, regression, coefficient. Now we talk about regression. So even though these words are used in each other's terms, correlation is going to help us do what? It's going to help us find the equation of the line that best fits the data. Why do we want to find that equation? Very good. We use that equation to predict future values of the data. Because if there's a strong correlation, then we see that X's and Y's grow together or going down. Then we can put an equation of a line through there. Once we find that equation of a line, then we plug in the values in there. What kind of lines are going to be? Remember, we're talking about what kind of regression? Linear correlation regression. We always talk about linear. It's linear. The equation is a line. Call the regression line. Remember the equation of a line from algebra? What is it? Very good. Y equals mx plus b. That's the equation of a line. Where m is the slope and b is the y-intercept. Or where it crosses the y-axis. So there's the x and y are gonna be the same. Those are the variables, like the shoe and the height. M is going to be how they're related to each other. So it could be, like, in essence, we're talking about the R there. And B is where it crosses the y-axis, or our first data set. Let's define what a regression line is. The regression line is the line of best fit. You'll also hear it called the least squares line. Is the line of best fit that represents the scatter plot as a line. So it's a line. It's that.
I'd be mad at how much it takes just to make it just clear.
Oh, well, no, it's just that in mathematics, everything has more than one meaning. When we say slope, what are all the uses for a slope? Well, we can find slope is also a rate of change on how much, if I have data, how much did my is my gas mileage in my car? Is it getting better or worse? Compare it to two different times. How many miles of gas, how many gallons of gas did you use? How many miles did you go? How many gallons did you put in there? Keep on doing that, you can see what the rate of change is of your mileage. Your expenses. You can look at how much your electricity or your food bills are going up as time goes on. So that's what people do.
So you, in a case like, sorry, I mean, in a case like that, you your grocery bill as the data.
Because you see how much do I spend each month. And you see if you usually buy the same stuff every month, or your electricity bill, or your TV, your phone bill, all those bills. Plot those, get the last year's worth of data and look how much has been going up and going down. Usually they going up, not never down. They usually like the electricity bills, they give it to you in bar charts, in bar graphs. When do you use the most electricity? Obviously in summer. We're lucky that our winters are very mild usually, but in the north it's just the opposite. It's in the wintertime, they have to blow the air conditioner and the heater on, so the linear equation the linear equation is y equals mx plus b. Our regression equation is y kappa b sub 1x plus b sub 0. Where b sub 1 equals your slope, the rate of change, and b sub 0 is your y-intercept or your initial data when x equals 0.
Instead of top of Y, right?
It's called a cap. It's actually called kappa. It's just a pointy thing going up. Yeah, it means this is the y value of this regression equation. Because you'll never use the cap in anything else but regression equations.
What do you mean?
The same as, remember, mathematics is a language, X bar. No matter what country you go to, what textbook you ever read, if you see X bar, you know that means the mean or the average. When we'll learn some more symbols next week. So. Oh, yeah, this is the vertical axis. Here's the example. This is our last example. Regression line. The figure below shows a graph of example 5, we just looked at, with a regression line included. We calculate the values of B1, B0. That will be another story. So putting it in there, we get y cap equals 3.22x plus 80.9. Remember, this value here is the y-intercept. It's going to tell us where this line crosses the y-axis. It's the y-intercept. So if we keep on extending this line out, that's going to be 80.9. The slope, the B1 value, is 3.2, which tells us from one point to the next on the average. Remember, slope is rise over run. So it goes up 3.22 units and over 1 unit. But looking at this, what do we notice? The data is pretty far apart. The R value of this is 0.813. So do we say it's a strong correlation, weak correlation, mild correlation? The p-value is 0.0. Very good. But the critical R, that's more important, is 0.31. How does that relate to? Remember, our values have to be between 1 and -1, right? And there's 0. So if our critical value was 0.312, that means if I take 1 and subtract 1 minus 3.12, we get 0.886. So this is 0.688 and negative 0.688. So those are my critical values. Is my R value in one of these? My R value was 0.813. So my R value is here. So it tells us what? There's a correlation. Since we know there's a correlation, we could look at the graph and then objectively say, because it's so spread out, it's not a strong correlation, it's not a very strong, it's a somewhat strong. It has a correlation, but it's not strong. So that's how this stuff fits together. The problem is, how do we find the numbers? That's what we do next week. And that's it for today. That's all she wrote. I know, did I confuse you all even further?